Hello everyone, we're going to keep talking about numerical distributions. We're continuing in chapter 2 with section 2.2 entitled Summarizing Important Features of Numerical Distribution. So if you'll recall from the last section, there were three sort of main features we said we always want to talk about or describe when we're looking at a numerical distribution. So the first one we said was the shape of the graph, and we'll get a little bit more in detail what we mean by that in just a second. The center or a typical value for the data, and finally the variation. So how spread out is the data? So I tend to use those words interchangeably: spread, variation, variability, so forth. Those all really mean the same thing. But let's get into some of the details here. So when we talk about shape, we're looking basically at two things, two possibilities. Is the distribution symmetric? And I don't have much room here. Sorry, it's a little messy. Symmetric, or is the distribution skewed one way or another? Another thing we want to look at is how many mounds there are. Literally, how many peaks or mounds in the graph there are. And then finally, are there any unusually large or small data values present that would indicate an outlier? So let's look at an example here of what it is we're talking about. Clean this up a little bit. Small. All right, so this graph. So we've got, these graphs here. Here's an example of what we mean by symmetric. You might have heard people refer to something as a bell-shaped curve, and that's basically what we mean. A graph where most of the data is clustered towards the center, and then it kind of tapes off in ways that it's even on both sides. It may not even taper off, but the point is the left and right side are symmetric to each other. A graph that's skewed will have more of the data in one side or the other. So you can see in this graph, most of the data is sort of left side, and then it sort of tapers off as the data goes on. So we would call that a right skewed graph, and we'll talk more about why it's right skewed in just a few minutes. When we talk about mounds, we're talking about peaks or clusters where there's a lot of data in the graph. So in this graph, this is symmetric again, but we also notice there's really just kind of one peak or one mound where all the data is centered. And it's a little subjective as to where we identify it, but in this graph, I mean, you may look at this bar right here, but right in the center, we've got a mound of where the data tends to accumulate. In this graph, this graph we would call unimodal, so uni means one, so one mode. In the second graph here, we've got an example of a bimodal graph. And so you can kind of see we've got two peaks. So we have a place where the graph peaks here, and then again where the graph peaks here. So we've got two sort of modes or mounds in the graph. Multimodal, if there's more than two, we tend to just say multimodal. So multimodal means there's more than two peaks. I suppose you could say trimodal if there's three, but generally when there's more than one mode, we separate them on different graphs. So those won't come up very often. The peaks can be different heights. So kind of like in the second picture, let me write that out, different heights. So kind of like in the second picture, this obviously is a shorter height than this graph, and that's okay. The point is we've got those two peaks in the graph which indicate two modes. Bimodal and multimodal data may indicate the existence of different groups. So different groups within the data. In this case, if that happens, it may be better to separate the data into two or more groups and give different graphs. For example, plotting men's and women's heights. That might have been what this picture was up here. We might have had a situation where we were looking at heights for both men and women. So traditionally women would be shorter than men, and so this might have indicated, that's what we're talking about here, this might have indicated the presence of one group, maybe women, and then this might have indicated the presence of another group, maybe men. So a lot of times when that happens though, we'll tend to separate them into two different graphs just to make it easier to read what's going on. Outliers. So outliers, we've talked about that term a little bit. So outliers, I think in your notes on the next page, outliers are extremely large or small values. So values that tend to be away from everything else. Data values that are outliers do not, sorry, this is a little messy, do not fit the pattern of the rest of the data. So they don't follow the trends of where the rest of the data is going. They're far away from the rest of the data. This is a little bit subjective, what's considered an outlier and what's not. One reason why we like to look at the graph is because it tends to make it easier to see, especially if we're looking at a histogram, it tends to make it easier to see, or a dot plot, where that point might be, or that individual data point might be far away from the rest. When observing extremely large or extremely small values, report the values. So you always want to report to the reader what outliers you may have noticed in your data. Realize that they could be errors. They could be the source of an error. Sometimes we might collect data and somebody mistypes a number, and so we have an outlier that's really unusual, but it's an error. Or somebody was dishonest with data. We have a survey question I've seen before when we get to our projects later in the course regarding credit cards and how many credit cards do you own. And I think one semester somebody reported that they own 100 credit cards. So that group reported it as an outlier, but with the caveat that that's probably not an accurate number. So a lot of times outliers indicate some kind of error or mistake in the data, but genuine outliers are usually interesting data values. So here's just a quick example. We've got a histogram here. I'm not sure what this represents. I didn't give you much information about the data, so I don't want to say too much about this graph, but an example of an outlier that you might see on a histogram. So you can see that this section right over here is far away from the rest of the data. So this would be some kind of an outlier for this data. So let's get back to shape for a minute and let's talk about the shape of each of these graphs in this example. So in picture A, it looks like we're looking at salaries of some kind of data on salaries. And you'll notice that more of the data is in the lower end of the graph, and then it kind of tapers off as the salaries increase. So the shape for this, we agree it wouldn't be symmetric. This would be skewed, and we would actually describe this as skewed right. So when we talk about skewness, you always describe it in terms of the tail. So because the tail is on the right side, that's where the data tapers off, we would say it's a skewed right, or right skewed graph. In this picture, we're looking at test scores, and you can see that more of the data is in the higher end of the test score range. And so we've got more data here, but the tail is on the left side. So this would be a graph that we would describe as skewed left. In picture C, you can see that we've got a roughly symmetric graph. There's a little bit of subjectivity sometimes when you describe something that's symmetric versus skewed, but with symmetric, you may have some unevenness in the graph, and that's okay, but we're basically looking for symmetry on the left and the right side of the graph. There's not a bulk, or there's not a section of the graph where on the right or the left side the bulk of the data lies. Instead, the data lies somewhere in the middle. So this would be an example, and I'll even put in the word roughly symmetric. Real data is not going to be perfectly symmetric, but we tend to have something that's close to it, so we'll say roughly symmetric. So the next example, it says, what shape would you expect to see in a histogram of the following data sets? So let's look at the data here. So there's 4 scenarios here, and I want you to think about what the data would look like if we were to pull a sample of each of these data sets. So A says the GPA of college students at Harvard University. I picked Harvard University because I'm thinking if you're at Harvard, you're probably a really strong student, and so your grades are probably pretty high. Most students probably have a GPA that's above, I would venture to guess, 3.0. This would probably be true at most universities because college students in general take their grades pretty seriously, but I really didn't want there to be any ambiguity about the level of students. That's why I said Harvard. So if you think about a graph that has GPAs that are high, most students have GPAs that are high, think about it in terms of a histogram. I think that's the easiest way to do it. So the higher GPAs would be on this end of the graph. So like if this is the 4.0 range, and down here we would have the 1.0 or whatever, most of your students would probably be up here above a certain number like 3.0 or whatever. You might have a few ends that have a lower, or a few students have a lower GPA, but most are on the right side. So we would say that the graph here is skewed because it follows the tail. That would make it skewed left. SAT scores, Part B. SAT scores nationwide. The SAT is a standardized test. Standardized tests generally have Some students who score really poorly, some students who score really high, but the bulk of students are somewhere in the middle. So almost every time you see a question about a standardized test, the distribution is going to be roughly symmetric because most students are going to score somewhere, let me get rid of this, most students are going to score, somewhere in the middle. You may have some students who score really well, some students who score really poorly, but most students are going to fall somewhere in the middle when you're talking about a standardized test. And so standardized tests are generally symmetric. Income of U.S. residents. So this might be different depending on what part of the country you're looking at. But if we're looking at the entire country as a whole, most people are lower than, I'm throwing a number out, say $50,000, even $100,000. Most people are going to be making less money. You might have some people who are rich, but most people are going to be below a certain amount. So if we're looking at salaries, most of the data is going to be in the lower end, and then you'll have some wealthier people that have higher salaries over here. But most people are going to be below a certain cutoff and have salaries down here. So what does that indicate about the graph? That means it's going to be skewed right. And then the last question here, last digit of Social Security numbers for a random sample of people. I use the word random here because I want you to think if we're just pulling numbers randomly, 0 through 9 for a digit, they're going to all come up at an even amount. So this would be what's called a uniform distribution. So, and if it's uniform, let me see if I can get a picture of this really quickly. So very, very, very rough sketch here. But if we're looking at digits of Social Security numbers, say 0 through 9, if we're doing it randomly, we have an equal chance of selecting people with a digit of 0 versus people with a digit of 9. And everything else in between is going to have an equal chance of being selected. So we would describe that as a uniform distribution. They're all the same. And for that reason, we can say symmetric. And we can go over that one again in class if that's a little unclear what we're talking about. As long as the first three make sense, that's what matters right now. So we've talked about shape, so we can describe shape in terms of skewness or symmetry, in terms of any modes that the graph might have, unimodal or bimodal. The next thing we want to talk about is the center. So the center, remember, is just a generic term for a typical data value. Okay, so a typical data value. So something that represents the data, something that's a good indication of what represents that data. And right now this is a little subjective. When we get to chapter 3, we'll have some more concrete ways of identifying what the center is for different types of data. But for now, let's just remember it's a little subjective. You can give me an answer that's either a single number or you can give me a range of numbers. It's kind of up to you. When we work the problems in my math lab, you'll see how they want you to answer them. Let's look at an example. So estimate the center or typical value for each of the graphs below. This could be, like I said, a single value, or you could give me a range of values. It's a little subjective right now. So one good way to think about this is to think about, okay, we're looking at salaries here. Notice that this graph is skewed right. Salaries tend to be skewed right. So we're looking at, one way to think about this is where the halfway point is in the data. That's one possibility. The other way to think about it is really just to look at the graph. Where is most of the data located? And you can see, because this is a histogram and the tallest bar is right here, somewhere in the $2,000 to $3,000 range, we would say the salary here, the center or the typical value, you could tell me is $2,000 to $3,000. If you want to include this next section of data, you could even say $2,000 to $4,000. That would be acceptable as well. If you're looking for a specific number, you could go halfway. You could say 2,500 or 3,000 or something like that. Any of those would be acceptable for where a center or a typical value is. How about in the next example, we have a graph that's skewed right again. So you want to think about where is the majority of your data, what represents the majority of the data. This is the tallest bar, so this looks to me like it starts at 95. You could say 95 to 100. That would be an acceptable answer. You could say 90 to 100 if you want to include the second bar right below it, or you could even say 95. I would accept any of those answers as a typical value at this point. And then the last thing we want to look at is the variation or the variability. So we're looking at the horizontal, how far out, horizontal spread in the histogram of the data. Are the data points really far out, or are they all clustered closer to each other? This is a little bit subjective. A lot of what we're doing is a little subjective, which is maybe a little uncomfortable right now. But the more we go through this, the more we'll come up with some concrete ways. Right now, I just want you to get a sense of what to look for in the graph. And so for this example, one thing we might ask you to do is to compare variability. Later on, we'll have some concrete ways using standard deviation and some things like that to help us say for sure how spread out a graph is. But for now, you can just kind of eyeball it. We're looking at, I don't know what this data represents, we should have labeled the graphs, but we're looking at two graphs, and I want you to just kind of eyeball it and look at which one seems to have the larger spread. Which one is the data spread out more? One way to look at this is to look at the range. So the range would be the lowest to the highest value. So you notice in this first graph, the range of the data goes from 62 to about 65. In the second graph, what is the range? This time, the data starts out at 60 and goes as high as, looks like maybe about 70. So because this one has a larger range, and you can also see we've got more gaps in the graph, literally there's more space in the graph, we would say that this one has more variability or more horizontal spread than the first graph. So to summarize, when we're talking about a numerical distribution, I want you to remember there are three things we're generally going to describe them or compare graphs in terms of: the shape, the center, and the variability or the spread.